In a previous video, we talked about how metallic bonding can be represented as an array of positive metal ions surrounded by delocalized valence electrons. Sometimes this is referred to as a sea of electrons model. What this means is that the valence electrons in the s and p orbitals are shared amongst the cations in the metal. They don't just orbit around one atom, but they move freely throughout the spaces between the metallic ions. Many of the unique properties of metals are explained by this arrangement, including the following. Metals tend to be shiny and reflect light. Metals tend to conduct electricity, which makes sense since the electrons can move freely through them. Metals are ductile and can be pulled and stretched into wires without breaking. Metals are also malleable, which means they can be compressed or pounded. This simulation shows a hammer pounding a piece of metal. Although the cations shift a little bit as the metal bends, because the electrons are shared, the bonds are easily broken and reformed, and the metal doesn't break. This is very different from what happens in a crystalline lattice formed by the ions in ionic compounds. When ionic compounds are hit with a hammer, they shatter. In this picture, you can see how shifting the structure of an ionic crystal results in anions repelling anions and cations repelling cations. Ionic solids are very brittle, but metal crystals, yes, we call these crystals too, they don't break because of this electron sea structure. Metals are also good conductors of heat, and they have high melting points and boiling points. That's because of the crystalline lattice structure. There are lots of electrostatic forces that you need to break in order to melt a metal. Now let's talk about alloys. An alloy is a mixture of elements, at least one of which is a metal. There are two main types of alloys, interstitial alloys and substitutional alloys. Interstitial alloys form between atoms of different radii, where the smaller atoms fill the interstitial spaces between the larger atoms. We will often represent them like this. The main thing to notice is that the particles are of different sizes. Steel is an example of an interstitial alloy formed from iron and carbon. The tiny carbon atoms fit in the spaces between the much larger iron atoms. Substitutional alloys form between atoms of similar radii, where one atom substitutes for the other in the lattice. One example of a substitutional alloy is brass, which is formed from a mixture of copper and zinc. You can see that copper and zinc atoms are similarly sized. It's also possible to have an alloy that's both substitutional and interstitial. Stainless steel is one example. The carbon atoms fit into the spaces between the iron atoms, which make up the bulk of the lattice. However, some of the iron atoms have been replaced with nickel and chromium. Alloys have different properties than the pure metals they're made of. For example, steel is stronger than iron. It also doesn't rust the way iron does. Since aluminum and titanium are very light, they can be used to reduce the mass of metals they form alloys with. This is very useful when it comes to building airplanes or trying to get better gas mileage. Alloys that are made of two metals have no single melting point. They melt over a range of temperatures. This can be very useful in industry. You should now know about metals and their properties. You should know about metallic bonding and the sea of electrons model. And you should know about the two main types of alloys, substitutional and interstitial.